Welcome to everybody. This session is about eShape, which is a European Euro-Geo project, which is supposed to showcase what we do in Europe for geo. We have over 30 different pilot services who are being developed in this project that already started in 2019. There are 7 different showcases, and here we want to concentrate on the climate showcase. But there are also showcases for renewable energy, agriculture, water, health, the ecosystem, and disasters. But climate showcase pilot services, which we will present here, are 4 of them. We actually do have 5 because one is improving carbon fluxes for oceans and land areas. But we want to here concentrate on the ones who have seasonal forecast included, because this is an interesting news, let's say, data set which has a lot of potential, but it hasn't been used so much yet. So we try to see what and how much seasonal forecasts can help different sectors. And these seasonal forecasts are available for openly and for free from the Copernicus Climate Change Service. And there's a link if people are interested that they can go and check it out. But seasonal forecasts in that sense are different when weather forecasts. That they are ensemble forecasts means that there are, for example, 51 different forecasts for the same time period with the same variables, but 6 months ahead. And these will be updated only once a month. And for seasonal forecast in general, it is very important for almost any application that you need to take care of something which is called bias adjustment. So you have to try to say, for example, 20 years of past kind of weather situations, and for this particular variables that you correct them with these statistics for the different points where you are looking at it, because seasonal forecast information is pretty coarse and there's a lot of more detailed information that can be corrected into these forecasts afterwards. And you can see on the right side a little bit these kind of 51 different graphs for seasonal, for soil wetness, soil temperature, and for snow height from a February forecast. You can see that the forecast is not just one line, but it's the bunch of many. And the idea is to see how much can you do from there using the probability of results. But let's go to the pilot services. So we have 4 lined up. Urban resilient harvester seasons, hydropower from snow, and seasonal preparedness. The presenters are next to them, and I will always present them first. But now we start with the urban resilience pilot, and Saskia Buchholz from the German Weather Service will start. So please, Saskia, go ahead. After each presentation, 1 question, and at the end we can discuss more. So, Saskia, please, you start.
One moment, I will share my screen. Can you see my presentation?
Yes, we can.
Yes, okay, perfect. Yeah, also good morning from my side. My name is Saskia Buchholz. I'm working at the German Meteorological Service, and I will now give you an overview on our free pilot applications that support the urban resilience and which are developed within the eShape project. I would also like to thank my colleagues from the Finnish Meteorological Institute, from the Zentralanstalt für Meteorologie and Geodynamik, and also from the German Meteorological Service, who helped to develop the pilot applications. The goal is to strengthen the urban resilience and to be prepared for extreme weather situations. And the different pilots use different data. For example, subseasonal and seasonal data sets for the FMI and ZAMG-Pilot, and the ZAMG uses climate projection data. And now I will give you the short overview of the 3 pilots. So the pilot from the DWD uses seasonal forecasts, and the products should be tailored for the city authorities to help them to plan and prepare for severe heat waves and also for dry spells. So we had that during the last 2 years. We had long-lasting heat waves and also dry spells over whole of Germany. And yeah, the water is scarce and the resources has to be distributed among the different sectors, and the product should also help the city authorities to distribute among the city boundaries. The product produces maps, time series graphs, and tables, both as an ensemble mean prediction and also as a probabilistic prediction. Right now, we are only using the German climate forecast system, which has a very coarse resolution like the other ensemble members also. And we would like to increase the resolution via a statistical downscaling approach to a goal, or the goal resolution is 5 kilometer by 5 kilometer. The seasonal forecast products are developed for the 16 state capital cities in Germany and for our pilot co-creation partner, the city of Aschaffenburg. And all products will be available at our climate prediction website. The statistical downscaling approach and the first products for temperature and precipitation will be operational by the end of this year. Here you can see the time series graphs on the left-hand side for the ensemble mean prediction and on the right-hand side for the probabilistic prediction. And on the up of the right-hand side, you also see the map showing, for example, the 16 state capital cities of the German states. With the prediction come also a prediction skill by the form of a traffic light showing if the prediction is significantly better, comparable, or worse compared to the observed climate mean, to give you just an information about the skill to make better decisions. The FMI pilot uses subseasonal and seasonal forecasts, and the product is tailored for winter maintenance activities and tested by the city authorities in Helsinki. It should help to plan their activities and to improve the winter safety on the streets and optimize the maintenance costs of the authorities. During the co-creation process, there was a close collaboration with the city authority of Helsinki. And together, FMI and the city decided for the following products or variables. So there is the snow accumulation for 6-week outlooks and also monthly outlooks, 3 months ahead. And the long periods of freezing and mild weather, the slippery conditions, and the conditions for the spring street cleaning, they are available as a 6-week outlook. And the graphs of the 6-week and also the monthly outlook are describe the likelihood of the expected weather conditions through the probability forecasts. And the skill of the forecast is furthermore improved through a bias adjustment of the variables. And both the subseasonal and the seasonal outlooks are running operational on different servers. For example, the FMI server for the subseasonal outlooks and the Vikeo Dias platform for the seasonal outlooks. And the products are available on the Ilmanet platform and also the web portal of the seasonal.fmi.fi website. So everything is available online. Here you have, or you can have an idea from the figures, how the 6-week and the monthly outlooks look like. For example, the 6 weeks outlook, the forecast spread is shown by these wireline plots for every week. And the dotted line presents you the climatology that is behind the data. And the 6-week updates are updated twice, or the 6 weeks outlooks are updated twice a week on Tuesday and on Friday. And the whole testing phase of the service is completed now. And the usability of the service was tested during the winter season by the city of Helsinki. And now the service is improved based on the users' feedback. The ZAMG-Pilot uses climate projection data, and the products are available for various Austrian cities. And the focus here on the product is the summer heat load. and it should help the city authorities for the urban planning process, for a better risk management, and also for environmental protection. And the application shows high resolution maps with heat load information for the different cities and different climate projection scenarios, which are based on the RCP, the representative concentration path scenarios, for example, the 8.5 or 4.5 and 2.6 scenarios. The products provide consistent representation of the spatial patterns in the heat load, and the product is also evaluated or will evaluate the differences in the model results and provides a standardized modeling output. And the product and the climate projections are available at the data server from the Climate Change Center Austria. And the data are provided in different formats. As you can see here, there are maps available and different figures. You can also download the data. I hope you can see this little animation. So here, for example, you can see a time series of annual summer days for the city of Vienna. You can change between the different time periods, or as you can see here, you can have a look like a film, and the time varies between 2011 to 2100, so at the end of this century. And here, as an example, you can see the results for the representative concentration pathway 4.5 and a combination of a global climate and regional climate model here from Meteo France and the Swedish Hydrological Institute. And the data are furthermore interpolated and downscaled via statistical approach and the combination with a microscale urban climate model, so that you also have the information of the urban heat load on a very high resolution. So that's from my side with the presentation. And yeah, if you have questions, please.
Yes, please write into the chat if you have a question. So we can pick one up now, and then the rest we will answer during the presentations of others into the chat, or afterwards we can discuss them. So any of the participants has a question, please write into the chat. But as I don't see any in the chat yet, let's move on to the next presentation. Miriam Kosmale, please go on with your pilot. Harvest the seasons.
So then let's share the screen. So I think you can see now my screen on full mode.
Very good. Go ahead.
Okay, so thank you very much that I'm getting the time to present the web application Harvest the Seasons on behalf of our team of Finnish Meteorological Institute Arctic Space Center. Principal pilot developer is Mikko Stralendorf, our session lead now, and me as pilot coordinator, with the collaboration of our colleagues Mikko Moisander, Tuomo Smolander and Jaakko Ikonen. I will be presenting Harvest the Seasons, which is a service on forest trafficability. This service was developed within the climate showcase in eShape and focuses on the forest condition based on climatological and meteorological forecasts. First, a few words about our institute. We are the National Meteorological Service of Finland, which is the administrative branch of the Ministry of Transport and Communication of Finland. And our division, the Arctic Space Center, is responsible for operational activities of National Satellite Data Center and operational satellite and research services. All this includes observation and research data on the atmosphere, near space, seas, weather, air quality, climate services. And all our activities support decision-making on societal needs. Some background information. Most of the Baltic Shield, including the Scandinavian Peninsula and Finland, is dominated by forest, as you can see in the map. This map on the right-hand side is one layer in our service, Harvester Seasons, which we are offering. It's based on the Copernicus land monitoring service. 75% of Finland's area is covered with forest, with most of the population living in the southernmost cities. In the recent year 2020, a total of 78 million solid cubic meters of roundwood were consumed in Finland. Wood processing is still one of the relevant industrial sectors in Finland. With 2.7 billion euros of annual tax revenue, it plays a significant part in the country's economy. Goods from the forestry sector contribute with 1/5 to the Finnish export market. This covers paper, board and converted products, sawn material, pulp and wood-based panels. Let's start with two statements, one by the Ministry of Agriculture and Forestry of Finland. Securing sufficient forest resources and biodiversity, as well as climate change mitigation and adaptation, are among the key elements of sustainable use and management of forest. Sustainable forest management comprises the dimension of economic and ecological, social and cultural sustainability. And from the geostrategic plan, GEO envisions a future where decision and actions for the benefit of humankind are informed by coordinated, comprehensive and sustained Earth observation. Implementing GEOs calls on GEO to strengthen its focus on users and stakeholders and reaffirm support for geodata sharing principles. Why is a trafficability service needed? 99% of commercial timber harvesting is conducted with wheel-based forest machines. These machines are quite heavy, almost 40 tons when they are fully loaded, and require good load-bearing conditions for their operation. Depending on the soil-bearing capacity, operations with those heavy machines can lead to soil deformation and damage to the ecosystem. Soil moisture due to the actual weather condition lowers the bearing capacity for most of the surfaces, especially peatlands and clay-dominated soils, which are quite common in Finland, account for certain challenges during periods of snow melting or wet conditions. The number of deep ruts, which should not be bigger than 10 centimeters, caused by the heavy machinery, has to be kept minimal. This is the background information why we are developing this service. So about the status quo before the service was developed. Typically, the best time for forestry operation has been winter, when there is snow layer on the ground and the ground is frozen. In Finland, the share of peatlands from which wood can be harvested only in winter condition is high. However, good winters for harvesting have decreased. For example, this year has been an exceptionally cold and long winter, whereas the years before, the mild winter made harvesting operations planning quite challenging. Basically, from a wood supply point of view, the wood has to be harvested all year round. So the weather conditions cannot be changed, but the harvesting sites can be selected according to the best possible bearing condition. The Harvester Season service is built upon an already existing trafficability maps provided by the Finnish forest centers. Those mapping system consists of high-resolved mosaics derived from LiDAR measurements by Argonaut. The so-called Hydrological poisson maps have been used quite often in the recent years for operation planning. They have a 60 by 60 meter grid resolution and cover almost the whole country of Finland. It's categorizing the soil, the Finnish Finnish country into 6 classes depending on its soil structure and under which weather conditions those areas are best trafficable for these heavy machines. There has been extensive studies by Lukia and partners on the dependency of machinery, seasonal condition and rut formation, as well as soil compaction based on these issues. Nevertheless, those trafficability maps were still a static information and did not include weather or seasonal forecast information so far. Harvester Seasons is now combining this static information with 10-day weather forecast information and on a long term with seasonal ensemble forecasts. The soil conditions are considered differently between summer and winter condition. So this is a web service where the users can go, click and zoom along the map, get the time series and forecast for trafficability. We developed the service in collaboration with forest companies and developed an easy trafficability index, good or bad, depending on the different seasons, winter and summer. The summer condition is dependent on the soil moisture, and if 40% of the soil wetness is higher than 40%, then the soil trafficability gets a bad value. This is all analyzed based on the 51 ensemble members. The next slide is explaining that a little bit better. Here you can see the 51 ensemble members, which are also accessible in the service, just to get the background information, how the trafficability is calculated. The service is using seasonal forecast data in combination with a reanalysis bias correction. ERA 5 land and ZAMG seasonal forecast information is directly accessible via the climate data store and operationally connected to the Harvester Season service via the climate data store API. The service follows the geo-recommendation leveraging European scientific datasets and the data sharing principle. Harvester Seasons is using the European computing infrastructure as this is the way forward within geo initiatives and the European context. The service is running operationally on a Copernicus DIAS platform. We have built it on Wikio in combination with FMI's SmartMet data server set up in a Docker environment. Service products on trafficability can be provided on the fly while zooming and navigating through the web app service. A service is only valuable when it has users, of course. During the recent months, FMI has been in close collaboration with Metsäteho and had conducted extra effort in user interaction activities. Since some of the biggest key players and big group of stakeholders of the market are located in Finland, a lot of user feedback could be collected to tailor the service to the user needs. I show here just one example, which is a different color coding for colorblind people, which was a special request by the users. It was said that approximately 10% of the Finnish men have problems with the distinguishing red and green colors. So based on a user survey, we developed and implemented an additional color scheme. And of course, additional map layers were added to the service according to the user feedback. So I close my presentation with a statement by Metsäteho. The Harvester Season service brings long-awaited relief to consider continually changing harvesting condition in forest operation. Harvesting contractors welcome all sources of information that help with harvest planning to enable operation in poorly performing conditions at the right time. So as a summary, the service meet the requirements of GEO to be a coordinated, comprehensive and sustained Earth observation and service development, and give an added value to the economic and social impact. And below some screenshots of our layers. And on the left-hand side, you see the actual map of forest fire risk, since in Finland we have at the moment a heat wave. So on the left side, you see our forest fire index is southern Finland is almost red. So no forest cutting at the moment allowed in the Finnish forest. Thank you very much for your attention. And of course, give us your feedback either now or via the online form on the website or directly via email. Many thanks.
Thank you very much, Miriam. Very good presentation. Now, if there's one burning question, please indicate in the chat you want to raise it. Otherwise, because time is moving on, so I don't see any action in the chat. So let's go to the next presentation. You can still ask questions by typing it into the chat. Jaakko Ikonen will present the next pilot service. Please go ahead.
Yes, good morning. Okay. Okay, wait a second. Okay, there we go. Yes, so my name is Jaakko Ikonen. I also work for the Finnish Meteorological Institute and Arctic Space Center. So I'm gonna give a presentation about hydrological forecasting in high latitude basins and give a brief introduction or a summary of web service that we've built as part of the eShade project. So pilot number 4, I believe we are. So this is related to a basin in northern Finland called the Kemijoki Basin. So those of you who are not aware of where that is, which is probably most of you, it is there in the indicated area with the square. So that is northern Finland. So most of this basin is located above the Arctic Circle. So that in itself brings some basic challenges that are kind of specific to Arctic regions, which mostly are related to snow melt. So this the spring snow melt season is the main driver for peak flow in Kemijoki, and I would presume in other basins in high latitudes. So one of the problems is there's a lot of uncertainty in the spatial distribution of snow cover or snow water equivalent. And it seems that it should be easy to observe, but that's not always the case. So that's a bit of a problem for hydropower companies and for water management authorities alike. And another specific problem is actually the timing of snowmelt and the volume. And this, again, seems like something that should be quite easy to predict, but in actual fact, it has proven to not be that. So basically that means is that even small amounts of snow can cause quite high river discharge and floods and problems for hydropower companies. And on the other hand, even large amounts of snow can also, what they can do is like you might not get that high peak flow events, depending on how the snow melts and what time period and so forth. And it's proven to be sometimes quite difficult. Another specific problem in the north is frozen soil, and that can have an effect on runoff volumes, particularly in the autumn season. The problem there is, again, is the spatial distribution of frozen soil, because it's, and also depending on the soil type. So it's quite difficult sometimes to determine whether or not a soil is actually frozen or not. And also, what is the effect on hydrology? It's a bit unclear at the moment. So in some cases, it should, if you have frozen soil, what you should have is higher overland flow, which can lead to larger peaks in discharge. or in some cases, even if you have frozen soil, you can have sort of boreholes where the water, the infiltration rates would be quite high, which might actually mean that there's less overland flow. So that's actually it's a scientific question, and also it's one that's pretty difficult to assess over large areas. Then there's of course the addressing the uncertainties in long-term seasonal forecasting. Although this is not specifically related to high latitude hydrology, of course, this pretty much affects anywhere. So basically addressing that and how to communicate the uncertainties and how to even assess what those are. Another challenge is that, well, kind of a positive challenge is that there's an abundance of Earth observation-based and in-situ data related to snow cover and soil freezing. However, they're usually quite scattered around in different portals and different services. So for the end user, it can be quite difficult to gather all the data and interpret them. So there's a need to basically collect this data and then harmonize that into a single service. So the stakeholders for this pilot, naturally what I already mentioned, is a hydropower company and energy brokers, but specifically the end user for this one at the moment, or the primary end user, is Kemijoki Oy, and they are mostly interested in nowcasts and forecasts. Mostly it's short-term forecasts, but they do have a strategic interest also in seasonal forecasting. And also now we've also noticed that there's been more and more questions from the scientific community in general. So occasionally I get emails from various scientists around Europe asking for data, and because what they want to do is run their own models in this area and test different things, or they just want data for something else. So that's kind of a new sort of end user or stakeholder. So one of the ideas of this service is not just to provide sort of a visual, like basically a visual service where you can see what the conditions are, but also that you could download data and also historic data. So other scientists can produce different kinds of new models. And actually, us ourselves, not me, but a colleague of mine is working on machine learning techniques to predict stream flow. And so far, there's been very good results actually in that. And we will be adding that component to this service in the very near future, I'd say sometime during this summer. So anyway, yeah, so we built a web service to deal with these issues. So basically what it does is it provides a short-term 10-day deterministic hydrological forecast, and that's driven by ECMWF high-res meteorological forecast data. So that's a deterministic model. And then we also provide monthly 90-day seasonal forecasts with 55 ensemble members, and that's also driven by ECMWF CS5 meteorological forecast data. The service basically, it's formed of 3 components, or comprises of 3 primary components. So there's a land surface modeling part, which is driven by FMI's HOPS model that we've developed. So this is a spatially distributed 5 by 5 kilometer conceptual model, and it has sort of GIS database a priori parameterization. So what we're trying to avoid is building a model where we calibrate everything. So the idea here being that we could potentially move this model elsewhere with ease, basically, or easier. Sometimes these hydrological models require quite a bit of calibration and calibration data, making it very difficult. Yeah, and then there's also a Streamflow routing component. So the Streamflow routing component sort of links up the different land surface model grid cells to each other, producing Streamflow forecasts. And then we also have external data. So we're trying to collect data from various sources and providing those in our service, and also assimilating some of them into the HOPS model itself. And then there's also in situ observations that we are, again, collecting, and we'll be adding more and more of that to the service later on. So the component one, as I said, is a basically it's a land surface model, but it's based on something called the Sacramento soil moisture accounting model. So what it does is it handles soil moisture fluxes, and also we've added a soil temperature model to it, and it has 4 layers. So the soil moisture fluxes and soil temperature, they both sort of regulate surface and subsurface flows that go to the Streamflow routing model in the second phase. So each cell is modeled separately, so they're not connected to each other without the Streamflow, the HOPS routing model. So it takes, so this model takes as input precipitation and/or snowmelt, potential evapotranspiration, and 2-meter air temperature. So there's not very high data requirements to run this model, because that's also a problem in many areas around the world, and especially in high latitudes where there's not that many meteorological observations available. So the output is soil moisture for the top soil layer. So that's roughly, depending on the cell, between 0 to 20 centimeters. And then for the root zone, so that's something between 20 and 200 centimeters. We calculate soil temperature for 5, 10, 20, and 100 centimeters. And also the model gives infiltration and percolation rates, as well as actual evapotranspiration, and then the runoff component, which is comprised of 3 different things. So you have surface runoff, inner flow, and base flow. And I want to add as well that actually it's not in this slide, but peat bogs are modeled separately with a slightly different type of model, but it's the same HOPS model, but there's a different module for that. So you can see the output of the land surface model here. So this is the Webservice main page. So we provide them as 2-dimensional maps. So you can you can zoom into the map, pan around, and click anywhere to get data from a single point. So the reason there's 2 maps here is that the idea is that the user can compare 2 variables at the same time. Then you see the animation there that sort of gives you the trend. So it gives you a 20-day hindcast and then a 10-day forecast. And then there are these sort of helper points. And these are actually FMI meteorological observation stations, which gives the value of the selected variable, because sometimes the colors, you can't really tell like what is the actual value at that specific point. And it also gives you a sort of trend. So if those arrows are pointing down and are red, that means a lower trend. And if they're pointing up and are green, there's a increasing trend in that specific variable. So yeah, so you can click on any point in the map and it automatically produces plots for you. This is just one example. There's produces 30-day map, 30-day hindcasts, 90-day trends, 600 days, or you can just plot them out individually, these 2 variables that have been selected. So here, I believe there's an example of runoff and top soil layer moisture at a single point, sort of their relation to each other. It's just an example. You could also, the idea here also being that you could take, for example, satellite snow water equivalent and then model snow water equivalent and compare the 2. And hydropower company, actually they use this feature quite a bit, because they do sort of in situ field campaigns where they go and actually measure snow depth and snow water equivalent, and then see which one is more accurate, the satellite data or the model data. So the second component, so this is the Streamflow, HOPS routing model, so Streamflow routing model. And what this does is it conceptually links all these HOPS cells together. And the idea is it moves runoff from the upstream areas downstream to the basin outlets, where we have a predefined sort of forecast points. So what this model does is it handles river channel flow retention, and as well surface and subsurface flow retention for each cell. There's actually also another feature in this model that it handles dam operations or hydropower plant operations, but in order for us to use this, we would actually need the hydropower plant operation sort of rules. But those at the moment, I think there's sort of strategic information, and we just don't have access to that at the moment. But later on in the future, perhaps and we could move more towards a sort of a hydropower optimization web service at some point, but at the moment this is just to share information. Yes, and this the output of this model is of course river channel water volume and then also river channel discharge. So this again is the sort of the main page of the web service, and if you click from a drop down menu, you can see that there's like now a river network. So this sort of describes this, sort of displays the second component of the service. And again, you have the same trend points where you can see if there's an upward trend or a lower trend. And there are a few fixed forecast points that the hydropower company has asked for. So that they are displayed there. And if you click on one of those predefined points, what you get is more graphs with actual river discharge at that point. So we give a short-term forecast on the left-hand side and then the seasonal outlook on the right-hand side. And then we also provide a sort of long-term hindcast, and that's in the bottom. And I believe this is the last 3 years, if I remember correctly. So it gives it sort of a general overview of how well the model is doing in that particular spot. Actually, in this case, if you look at the top left short-term forecast, we're a bit off at the moment. So there is some issue with the model, and it's quite normal, and we just need to fix this. On the right-hand side, I don't think I'm going to go through this seasonal forecasting, these graphs, because they're quite complicated. It would take too much time to go through. But basically, just a very short overview is that what they do is they give a probabilistic sort of forecast for when peak flows are expected to occur and how large would those peak flows be. And they're also color coded so that for the first 30 days, you get everything that's in green. Then the next 30 to 60 days would be black. And then the last 60 to 90 days would be red. So the thing is, like, if you were to plot all the 51 ensembles, it becomes a massive spaghetti mess, which is it's impossible to interpret anything from. But basically, from this graph, you can see though that the green bar here is the highest. So that means for this particular period, it's most likely that the peak flow for this 90-day period will occur within the next 0 to 30 days. And then on top, you can just see the sort of 25th and 50th and 75th percentiles of, or sorry, quantiles of these ensemble forecasts. So yeah, and then the last component is the external data component. So at the moment, for Earth observation-based products, we're using Copernicus Globland Snow Water Equivalent, and this is assimilated into the HOPS model. We're also getting Copernicus Globland Snow Extent data. This is just displayed, not used in assimilation at the moment. And we are also in the process of getting ESA's Moss Soil Freeze-Thaw product and a new product developed by FMI, which is based on Sentinel data. And this is a high-resolution soil freeze-thaw product. We might be assimilating these into HOPS as well at some point, but for now, this summer, the main goal is just to have this data available on the web service. Yes, and then for in-situ observations, we're getting SYKE, which is the Finnish Environmental Institute's Streamflow observations, and these are used only for validation. And we're planning to also add SYKE freeze-thaw observations. So these would actually, this should be said here that those will also be used for validating both the satellite products and the HOPS model.
Can you please, Jaakko, finish soon?
Yes, this is the last slide. Actually, I want to show one more slide. So anyway, this is just a quick example of how the Earth observation data is used. So we can see here that the top graph, the red line is HOPS Streamflow without simulation, and then the green one was the forecast with a simulated sweep. And in the bottom one, and this was from the eastern side of the basin, and the bottom one is from the west side, And here you can see sometimes the simulation of sweep products helps, sometimes it does not. That's it from my side.
Thank you, Jaakko.
Sorry for.
Yeah, we are a little late, so no questions here, all in the chat. But Stavros, hit it, and then you have your 10 minutes as well. Thank you.
Yes. Thank you, Jaakko and Nico. So, yes, this pilot is a joint effort between the Finnish Meteorological Institute and the Academy of Athens. And I would like to thank the colleagues, Andrea Vaida, Mika Rantanen, and Otto Haivarinen from the Meteorological FMI. And also John Kapsomenakis, Panagiotis Nastos, Lida Dimitriadou, and Professor Christos Zerefos from the Academy of Athens. Now, the idea here is that in Finland, first of all, there is a practical question on when should the people change the tires in the vehicles due to when the snow and freezing season begins and it ends. And for this reason, FMI, together with Weiner, who is a tire company and is acting, it is the end user of this service, they have designed and developed a tailored sub-seasonal and seasonal application for safety winter driving conditions that is based on the initialization time and ending time of the snow, let's say, season in Finland. And on the other hand, in Greece, the Academy of Athens, together with INSETE, which is the Federation of Touristic Companies, Industries in Greece, we have developed a short-term sub-seasonal forecast that is tailored to the UNESCO Cultural Heritage Sites in Greece, and it is aimed to tourists. So now, if we go first for Finland, the goal is to focus on winter driving conditions and define how should the tire companies plan retail activities and also the customers to decide when they should go on and change their tires. So in close collaboration with Weiner, there is a sub-seasonal climate outlook that includes the winter tire season, the onset and the offset of the season, and also probability of snow cover, the snow depth, and the freezing temperature. All of these are parameters very crucial for driving safe in such a cold environment. And also the seasonal climate outlooks that go on forward for 1 to 3 months include the probability of snow cover and the freezing temperature. Now, the service is already developed and in second testing phase, going up to 2022. And it is presented in a simple form. It is running operational on the FMI. The input is from the ERA5 reanalysis and the ECMWF ensemble members. So you get static weekly maps, animated versions of the maps, and also if you want to go deeper, you have some more information on specific products. You can go on and visit the service. This is online and obtain the results. And the methodology is taking the input from the ECMWF forecasts. Bias adjustment and skill assessment is processed later on. And in the end, you get 3 months ahead forecasts for the probability of snow cover outlook. You can see an example here for October, November, and December 2020. So you get different areas with the contours and so on, and you can help the interested end users you can assist them to take the necessary decisions for their services. And industries. As we said already, the service is up and running. You can go online and explore it and check for yourself. And now moving to a warmer environment in Greece, from Finland to Greece. Here the idea has to do that someone that is visiting in Greece, or someone that has a small business or a touristic industry running in Greece, you may need to take some decisions on which places are better to visit on a specific time of the year, on the next few days, or things like that. So we have long discussions with our users here in Greece, in the INSET Federation, and we have come up with a simplistic output that can be easy to understand by the public, and both seasonal and short-term forecasts are provided. At this time, the forecasts are for specific monuments of cultural heritage in Greece that are included in UNESCO Cultural Heritage list. And this is based on the climatological information from the ERA5 and the ensemble members of the C3S Copernicus Service seasonal forecast, and also high resolution WRF model running at 4 by 4 kilometers grid space over Greece. So as I said previously, we have selected these specific sites in Greece, and the practical question is that someone may have, I don't know, a couple of days, and you need to decide which way to go. You may visit Mount Athos, Philippi, the Acropolis of Athens, Olympia, Delos, Epidavros, I don't know what. So one of the things that one could also take into account is weather and climatological conditions. So the site is also up and running. You can visit it here in UNESCO/weather.gr, and you can switch between 4-day and seasonal forecast for specific sites, and you get different looks. You get a summary of the next day's forecast with simple symbols that we hope that one can easily interpret and understand. So you get an example here for Acropolis, again Corfu, with temperature, sunshine, and things like that. There is also a short description of each specific site that might also help the interested user to go on with their decisions. For example, here for the site of Delphi, you get the next day's forecast also in a summary. Then you can go deeper and explore some time series that are obviously more interesting also for our scientists to check that everything is working properly, but also for the interested user. So you get time plots of temperature, precipitation, relative humidity, and wind speed for each site. And then you can also go, of course, for the seasonal forecast for the next couple of months, again in the form of a short summary for the next coming period, and also in the form of a combined plot, including the climatological conditions for each site, and the C3S forecast that shows you that you are, I don't know, a little bit higher than normal, the temperature a little bit lower, or business as usual for some sites, things like that. And also for precipitation, and also wind speed. Obviously, you can go inside and browse between the stations. You can also get the forecast in a simpler summary form. Here for the Acropolis, Aegean and Corfu, again for the next few months. Actually, that was for the previous next months, the previous forecast. And in short, the service is up and running. We have discussed a lot with Inset, the end users here, who are happy with this application, and we think that this could be also be expanded to other sites in Greece and probably also abroad. And with this, I would like to thank you and pass the microphone back to Miko. Just a moment.
Thank you, Stavros. And thank you to everyone. Now, time is unfortunately up, so I guess we don't have time for actually questions, and the chat anyway didn't produce any. So I just want to thank every presenter, everybody who listened in. And let's remember these are videoed, so in essence, people can watch them later on. And I want therefore to say here, the main message for a geosymposium is, even if we have done them for our countries in Europe, we are very interested to kind of expand to other places and find partners around the globe to help develop something similar in other places. So please contact these presenters and the contact informations they have in the presentations. If you're interested, I'm sure that we will all react positively and be enthusiastic about a global collaboration. But thank you very much for this session, and go to the next one. Enjoy. Thank you. Bye-bye.